Hello there. Today I'm going to be going over understanding Bézier's curves and their applications as the report of the first quarter of the second semester. The scope of this quarter's study was mainly about vector spaces, eigenspaces, orthogonal projections, along with applications of these concepts such as least square solutions and least square error, along with other applications and concepts. However, the scope of this report is going to be directed towards a more engineering and geometry related aspect of linear algebra. These are the three main points that we are going to go over. First, combination of vectors, and then we will go on to discuss the construction of Bézier's curves, and then we will end up with applications of Bézier's curves. One of the key fundamental concepts that we were introduced to in the very beginning of linear algebra was linear combination, which we defined as adding together two vectors or more multiplied each by their respective scalar or constant in order to come up with a whole new resultant vector. However, today we want to introduce a relatively new topic, which is affine combinations. And basically, affine combinations are really a form of linear combination. However, the only exception is that the summation of all of the respective scalars for each vector must add up to unity. They all must be equal to 1 when added up. And the set of all possible affine combinations are said to be the affine span or the affine hull. Just like we were calling the all possible set of linear combinations span, we're calling this affine span or affine hull. Now, since we can describe the set of affine hull as C1 V1 plus C2 V2. I mean, if we're talking with these two vectors, V1 and V2, we can say that we can get rid of C1 and replace it by 1 minus C2, because we know that C1 plus C2 is equal to 1. So here, this must end up creating a line extending from V1 to V2. Because now we're talking about vectors as being points in space, and the two extreme possibilities of C2 would be 0 and 1, and 0 would make would end up with V1 as the result of the affine combination, and 1 will make the result equal to V2. Now let's move on to Bézier's curves. When thinking of Bézier's curves, it's better to visualize vectors as points, just as I mentioned earlier. And each point should define like an aspect of the curve. Each point is called a control point. And the curve is said to be the affine hull of all control points. So here, let the 2 points be P0 and P1, or P0 and P1. So hence, we can say that the affine hull or the affine span is equal to 1 minus t multiplied by P0 plus t multiplied by P1. And each different value of t would end up will end up landing on a new point in the line extending from P0 to P1. So as you can see here, with t equals 0.75, you will land on this point, which divides this line segment into 4 equal parts, 3 here and 1 on this side. Here you have t equals 0.5, which lands in the midpoint of the line. Here you have t0, which equals to P0. Now we can imagine that we add a third point, calling it P2, and between P0 and P1, we will have this point that's moving, and as we said, each one should describe a different affine combination. Now let's connect this point here with this point here, and let's let them slide with different t values. We will end up with this curvature right here, and this is our Bézier curve. The order of the Bézier curve depends on the number of points, the number of control points. So here we have 1, 2, 3 control points. This means we have 3 minus 1 order curve. So we have curve of the second degree, otherwise known as quadratic Bézier curve. Here we have 1, 2, 3, 4 points, so that's a cubic Bézier curve. The general formula for each of these Bézier curves are as follows. That's for the quadratic, and that's for the cubic. And in order to determine the gradient or the slope or the derivative of each point on the curve, you can simply take the derivative of the formula. So when talking about joining together two different Bézier curve, in order to achieve geometric continuity, as you can see here, you need to have the same value of the derivative at the point of joining these two curves. Now let's move on to the applications of Bézier curves. Bézier curves is of great significance when it comes to 3D modeling and game development. Why? That's because instead of having to deal with polyhedrons and millions of polygons and shapes, you can just instead of interacting with shapes and polyhedrons, you can interact with control points, which describe the curves or the curvature of different objects in the scene of a game, for example. And that makes the computer require significantly less time in computing and in dealing with the data. That's also of substantial significance when it comes to graphic design applications like Adobe Illustrator and Photoshop, because instead of having to deal with each curvature as a separate circle or as a separate ellipse on its own, and combining all of these peripheries together, you just deal with the simple points, the simple control points that define the curve. And that makes the job of the program or the software a lot easier. In order to get another type of understanding for how we might use the applications of Bézier curve, you might check out this video right here, which describes how Bézier curves can be used in animations and the making of cartoon. Thank you so much for listening, and see you soon.